Every single month, a single large-scale cricket farming facility can produce over 50 tons of protein-rich insects, the equivalent of more than 300 cattle in the same time frame, while using 99% less land and 98% less water. In just 6 weeks, a breeding population of 1 million crickets can multiply to become over 30 million harvestable adults, ready for processing into protein powder, whole roasted snacks, or animal feed supplements. How do these next-generation farms raise billions of crickets in climate-controlled facilities that operate with pharmaceutical-level precision? What automated systems and biosecurity protocols allow producers to harvest, process, and package millions of insects daily while meeting the same food safety standards applied to conventional meat processing? And why are American entrepreneurs, livestock producers, and sustainability advocates calling cricket farming one of the most promising solutions for feeding a growing population while dramatically reducing agriculture's environmental footprint? Welcome to AgriCraft, where we explore the innovations transforming American agriculture and building the future of sustainable food production. Today we are taking you inside the remarkable world of industrial cricket farming, revealing the breeding programs, environmental control systems, and processing technologies that make large-scale insect agriculture possible. From selecting the most productive cricket species and creating optimal growing conditions in vertical farming systems, through automated harvesting that processes millions of insects per hour, to food-grade processing plants where industrial machines transform whole crickets into versatile protein ingredients, we will show you every step of this cutting-edge agricultural revolution. All will be revealed in this video. Cricket consumption represents one of humanity's oldest food traditions practiced continuously across much of the world. Archaeological evidence shows that humans have eaten insects for at least 10,000 years, with crickets among the most popular species due to their abundance, mild flavor, and nutritional density. Today, over 2 billion people in more than 100 countries regularly consume insects as part of traditional diets, particularly in Asia, Africa, and Latin America, where cricket snacks remain common street foods and valued protein sources. However, Western cultures largely abandoned insect consumption centuries ago despite the nutritional and environmental logic. This cultural aversion created a blind spot in agricultural innovation, with research and development focusing exclusively on conventional livestock, while ignoring insects' remarkable efficiency as protein producers. The modern cricket farming industry emerged only in the past 2 decades as entrepreneurs recognized that Western food systems needed sustainable alternatives to resource-intensive meat production. Thailand pioneered commercial cricket farming in the 1990s, developing the foundational techniques that enabled scaling from backyard operations to industrial facilities. By the early 2000s, Thailand had over 20,000 cricket farms producing approximately 7,500 tons of crickets annually, primarily for domestic consumption and export to neighboring countries. This experience base provided crucial knowledge that North American and European entrepreneurs adapted when launching cricket farming ventures in the 2010s. The United States cricket farming industry has grown explosively since the first commercial operations launched around 2012. Today, American facilities produce over 3,000 tons of crickets annually, with production capacity expanding by 40 to 60% each year as new facilities come online and existing operations scale up. The market value of the domestic cricket industry now exceeds $200 million when including whole insects, protein powder, cricket-based foods, and animal feed applications. Industry projections suggest production could reach 20,000 tons annually within 5 years as technology improves and consumer acceptance increases. International comparisons reveal the global nature of this agricultural transformation. Canada has embraced cricket farming aggressively with large facilities in Ontario and Quebec, supplying both domestic and American markets. European countries, including the Netherlands, Belgium, and France, host sophisticated operations, producing insects for both human food and animal feed. Asian production continues expanding, with Thailand, Vietnam, and China operating some of the world's largest facilities. However, American operations lead in agricultural technology innovation, developing automated systems and quality control protocols that are establishing international standards for food-grade insect production. One shocking fact surprises even agriculture professionals familiar with livestock efficiency metrics. Crickets convert feed to protein approximately 12 times more efficiently than cattle, 6 times better than pigs, and twice as efficiently as chickens. This extraordinary feed conversion ratio means crickets require just 1.5 pounds of feed to produce 1 pound of edible protein compared to 20 pounds of feed for 1 pound of beef protein. When scaled to global food security challenges, this efficiency difference represents the gap between sustainable protein production and environmental catastrophe. The initial stage of cricket farming begins with species selection and breeding program development. While over 900 cricket species exist worldwide, only a handful prove suitable for commercial farming. The house cricket, Acheta domesticus, dominates North American production due to its adaptability to controlled environments, rapid growth rate, and mild nutty flavor that appeals to Western palates. Adults reach harvest size in just 6 to 8 weeks from egg, allowing multiple production cycles annually from the same facility infrastructure. Banded crickets, Gryllodes sigillatus, represent another commercially important species, particularly for operations targeting pet food and animal feed markets. These slightly larger crickets tolerate crowding even better than house crickets and produce more biomass per square foot of growing space. However, their flavor is stronger and less appealing for human food applications, limiting use in that market segment. Some facilities maintain separate production lines for different species, optimizing each for specific end markets. Breeding programs select for traits that maximize commercial viability, including rapid growth, high survival rates, docile behavior that reduces cannibalism, and uniform size at harvest. Unlike conventional livestock where genetic improvement requires years or decades, cricket generation times of 6 to 8 weeks allow rapid selection progress. Within just 2 to 3 years, focused breeding programs can dramatically improve population characteristics, increasing yields by 20 to 40%. While reducing production costs through better feed conversion and lower mortality. Breeding stock maintenance requires meticulous attention to genetic diversity and biosecurity. Commercial operations maintain separate breeding colonies, isolated from production populations to prevent disease transmission and ensure genetic quality. These breeding rooms operate under the strictest hygiene standards, with controlled access, protective clothing requirements, and quarantine protocols for any new genetic material introduced from outside sources. Maintaining diverse breeding populations prevents inbreeding depression that would reduce vigor and productivity over time. Environmental requirements for optimal cricket production are exacting, and modern facilities provide pharmaceutical-level precision in controlling every variable affecting growth and survival. Temperature represents the most critical factor, with crickets being cold-blooded insects whose metabolic rates directly correlate with ambient temperature. House crickets grow optimally between 82 and 88 degrees Fahrenheit. Temperatures below 75 degrees slow growth dramatically, while temperatures exceeding 95 degrees cause stress, reduce feeding, and increase mortality. Industrial cricket facilities use sophisticated climate control systems that maintain temperature uniformity throughout growing areas. Banks of heaters, air conditioners, and circulation fans work together under computer control to hold target temperatures within plus or minus 2 degrees throughout rooms that may contain millions of crickets. Temperature sensors positioned at multiple heights and locations feed data to controllers that continuously adjust heating and cooling to compensate for external weather changes and the metabolic heat generated by dense cricket populations. Humidity control is equally critical because crickets require moisture for proper molting, the process where growing insects shed their exoskeletons to accommodate larger body sizes. Relative humidity between 40 and 70% provides optimal conditions. Lower humidity causes molting difficulties that stunt growth or kill crickets, while excessive humidity promotes bacterial and fungal diseases that can devastate populations. Automated humidification and dehumidification systems maintain target levels, while ventilation systems provide fresh air exchange that removes ammonia and carbon dioxide that accumulate from cricket respiration and waste. Lighting programs influence cricket behavior and production efficiency. While crickets are primarily nocturnal insects most active in darkness, Research shows that specific light cycles optimize growth and breeding. Most commercial operations use 12-hour light and dark cycles, though some employ more complex programs with dawn and dusk transition periods that reduce stress and improve feed consumption. LED lighting systems provide full-spectrum illumination while minimizing heat generation and electrical costs. Housing systems for commercial cricket production have evolved dramatically from the simple plastic bins used in early operations to sophisticated vertical farming systems that maximize production per square foot of building space. Modern facilities stack growing containers 8 to 12 levels high in climate-controlled rooms, achieving population densities that would be impossible with conventional livestock. Each container, typically constructed from food-grade plastic measuring 3 feet by 2 feet by 6 inches deep, houses several thousand crickets at different life stages. Container design incorporates features that improve cricket welfare and worker efficiency. Rough interior surfaces provide grip for crickets as they climb and molt. Raised edges prevent escapes during handling while allowing air circulation. Removable egg-laying substrates simplify breeding management. Stackable designs with integrated feeding and watering systems allow high-density storage while maintaining accessibility for monitoring and harvest. The most advanced facilities use robotically serviced vertical growing towers where automated systems handle feeding, watering, and environmental monitoring without human entry into growing areas. Substrate materials inside containers provide hiding places that reduce stress and cannibalism while maximizing usable space. Corrugated cardboard arranged vertically creates thousands of individual niches where crickets shelter during daylight hours. This three-dimensional habitat allows populations 10 to 20 times denser than crickets could tolerate in flat, open containers. The cardboard also absorbs excess moisture and provides supplemental fiber in cricket diets. At harvest, workers simply remove the cardboard and shake crickets into collection bins. Nutrition programs for commercial crickets balance rapid growth against ingredient costs and final product quality. Cricket farmers have developed specialized feeds that optimize protein content, growth rates, and nutritional profiles in harvested insects. Most commercial feeds start with plant-based ingredients including grain meals, soy protein, wheat bran, and dried vegetables. These provide carbohydrates for energy and protein for growth, while keeping ingredient costs manageable at industrial scales. Supplementation with vitamins, minerals, and specific amino acids ensures crickets meet nutritional requirements for optimal health and growth. Calcium supplementation is particularly important because cricket exoskeletons contain significant calcium that must come from dietary sources. Vitamin and mineral premixes similar to those used in poultry feed provide micronutrients essential for proper development. Some producers targeting human food markets use organic feeds or specific ingredient combinations that enhance flavor or boost particular nutrients in finished products. Feed delivery systems range from simple manual distribution in smaller operations to sophisticated automated systems in large facilities. Conveyor belts transport feed to growing areas where metered dispensers deliver precise amounts to each container on programmable schedules. These automated systems reduce labor costs while ensuring consistent feeding that maximizes growth uniformity. Feed consumption monitoring helps identify health problems early, as reduced feeding often signals disease or environmental stress before other symptoms appear. Water delivery presents unique challenges in cricket farming because insects drown easily in open water, yet require constant hydration. Commercial operations use water crystals, gel-like materials that hold moisture while providing a solid surface crickets can safely access. Workers or automated systems regularly replenish water crystals, ensuring adequate hydration without drowning risks. Some advanced facilities use automated misting systems that periodically spray fine water droplets into containers, providing hydration while minimizing labor and water waste. Early care during the first 2 weeks after egg hatching determines long-term survival and growth rates. Newly hatched crickets, called pinheads due to their tiny size, are extremely vulnerable to environmental stress, dehydration, and predation from older crickets. Many operations isolate pinheads in dedicated nursery containers with especially fine substrate materials and enriched feeds that support rapid early growth. Survival rates during this critical period often determine overall production efficiency, with well-managed operations maintaining 95% or better survival from hatch to harvest. The harvesting stage in cricket farming involves collecting mature adults when they reach optimal size for their intended market. Timing is critical because crickets continue growing throughout their lives, and harvesting too early reduces yields while waiting too long increases feed costs without proportional weight gains. Most operations harvest house crickets at 42 to 49 days old, when individuals weigh approximately half a gram and have reached adult size with fully developed wings. Manual harvesting remains common in smaller operations, where workers physically sort through containers collecting adults while leaving younger crickets to continue growing. This selective harvesting allows multiple harvest passes from each container, spreading production across weeks rather than requiring complete population turnover. Workers use specialized collection tools, including nets and vacuum systems that gently capture crickets without injury. The most skilled harvesters can collect several thousand crickets per hour, though labor costs make this approach viable only at smaller scales. Mechanical harvesting systems have revolutionized large-scale operations, allowing processing of millions of crickets daily with minimal labor. These automated systems use vibration, airflow, and gravity to separate crickets from substrate materials and transfer them to processing areas. Containers dump onto vibrating screens that shake crickets through openings while retaining cardboard and debris. Conveyor belts transport collected crickets to processing facilities where industrial machines continue the transformation into finished products. Harvest timing increasingly relies on precise scheduling that coordinates growing cycles with processing capacity and market demand. Unlike conventional livestock that can be held at market weight for days or weeks, crickets continue consuming feed and can begin dying if not harvested promptly at optimal maturity. Sophisticated operations use software systems that track every container's hatch date and growing conditions, predicting harvest readiness weeks in advance, and scheduling processing plant operations to match predicted volumes. Live transportation from growing areas to processing plants requires careful handling that minimizes stress and maintains biosecurity. Even within single facilities, moving live crickets creates disease transmission risks. If contaminated equipment contacts clean growing areas, most operations use dedicated transport containers that never enter growing rooms, transferring crickets at centralized collection points. For operations shipping live crickets to distant processing facilities or customers, specialized insulated containers with ventilation and temperature control maintain optimal conditions during transport. The processing stage transforms live crickets into diverse products, ranging from whole roasted insects to protein powders and ingredient blends. This transformation requires sophisticated food processing technology adapted from conventional meat and grain processing industries. The first critical step involves rapid chilling that humanely kills crickets while preserving quality and preventing decomposition. Commercial operations use blast freezers that drop cricket body temperature to below freezing within minutes, a process considered among the most humane slaughter methods available for any livestock species. Frozen crickets move to washing and cleaning systems that remove any substrate residues, insect waste, or dead exoskeletons from molting. Industrial washing machines tumble crickets in food-grade water sprays, with multiple rinse cycles ensuring thorough cleaning. This washing is critical for food safety and meeting hygiene standards that allow cricket products to enter human food supply chains. Quality inspection during washing identifies and removes any dead or discolored crickets that might compromise final product quality. Roasting or dehydration represents the next major processing step for whole cricket products. Commercial roasting ovens similar to those used for nuts and coffee apply controlled heat that drives moisture levels below 10%, the threshold where microbial growth becomes impossible and shelf stability is achieved. Roasting temperatures typically range from 250 to 350 degrees Fahrenheit, with processing times from 20 to 60 minutes, depending on desired moisture targets and flavor development. Some producers add seasonings before or after roasting, creating flavored snacks that appeal to consumers hesitant about eating plain insects. Grinding systems transform whole crickets into versatile protein powders and flours that can incorporate invisibly into familiar foods. Industrial mills similar to grain processing equipment pulverize dried crickets into particles ranging from coarse meals to fine powders finer than wheat flour. Particle size determines end-use applications, with coarse cricket meal working well in protein bars and baked goods where texture is desirable, while ultra-fine powders disappear completely into smoothies, pasta dough, and other applications where consumers prefer not to detect insect origins. Protein concentration technologies create premium products with higher protein percentages and more neutral flavors. These processes, borrowed from soy and pea protein industries, use mechanical and chemical separation to isolate protein fractions from cricket flour. The resulting cricket protein isolates can exceed 90% protein by dry weight compared to 65% in whole cricket powder. While more expensive to produce, these concentrated proteins command premium prices in sports nutrition and functional food markets, where protein density and flavor neutrality are critical. Quality control throughout processing ensures products meet food safety standards and customer specifications. Temperature monitoring during roasting verifies that all material reaches temperatures sufficient to eliminate potential pathogens. Moisture testing confirms shelf-stable levels that prevent microbial growth during storage. Metal detection systems scan finished products for any contamination from processing equipment. Microbial testing of final products verifies that bacterial, yeast, and mold counts fall within safe limits established by food safety regulations. Allergen management represents a critical quality control consideration because crickets contain proteins similar to those in shellfish, and cross-reactivity can trigger reactions in shellfish allergic consumers. Processing facilities must implement strict protocols preventing cross-contamination if they also handle other food ingredients. Dedicated equipment, thorough cleaning between production runs, and regular verification testing ensure allergen safety. All cricket product labels clearly declare allergen warnings, advising shellfish allergic consumers to avoid cricket products. Packaging systems protect cricket products during distribution, while creating attractive presentations that overcome consumer resistance to insect foods. Whole roasted crickets typically package in clear plastic or glass containers that showcase product quality while providing necessary barrier properties against moisture and oxygen. Resealable pouches with zip closures maintain freshness after opening. Cricket protein powders package in opaque containers similar to conventional protein supplements, with scoop measures and nutritional labeling that mirrors familiar product formats. Labeling communicates required regulatory information, including ingredients, allergen warnings, nutritional facts, and safe handling instructions. Cricket products fall under standard food labeling regulations requiring accurate statements of protein, fat, carbohydrate, vitamin, and mineral content. Many producers include messaging about sustainability benefits and farming practices, appealing to environmentally conscious consumers who represent primary early adopters of insect foods. Cooking suggestions and recipe ideas help consumers overcome unfamiliarity and successfully incorporate cricket products into meals. Modified atmosphere packaging extends shelf life for some cricket products. Replacing air inside packages with nitrogen or carbon dioxide inhibits oxidation and prevents rancidity that can affect flavor during extended storage. Oxygen scavenger packets further protect products by absorbing any residual oxygen sealed inside packages. These preservation technologies allow shelf lives of 12 to 24 months for properly packaged cricket products, comparable to conventional protein ingredients. Storage requirements vary by product form and processing method. Frozen whole crickets require continuous cold storage at 0 degrees Fahrenheit or below, similar to conventional frozen foods. Roasted whole crickets and cricket powders are shelf-stable at room temperature when properly dried and packaged, though cool storage extends shelf life by slowing oxidation. Temperature control throughout the supply chain, from processing through retail sale, ensures product quality reaches consumers at peak condition. Distribution channels connecting cricket producers with consumers span from niche health food stores to mainstream grocery chains and online retailers. Direct-to-consumer sales through company websites allow producers to educate customers, gather feedback, and capture full retail margins. Online marketplaces including Amazon and specialty food platforms provide broader reach to curious consumers searching for novel proteins and sustainable foods. This direct distribution works well during market development phases when volumes are modest and customer education is paramount. Wholesale distribution through natural food distributors and specialty food brokers connects producers with retail stores willing to stock cricket products. These intermediaries have established relationships with retailers and understand the merchandising strategies that move unconventional products. Placement in health food stores, supplement shops, and outdoor retailers targets likely early adopters, including fitness enthusiasts, environmentally conscious consumers, and adventurous eaters who enjoy trying new foods. Mainstream grocery penetration represents the ultimate goal for cricket producers seeking to scale production and normalize insect consumption. Several North American and European grocery chains now stock cricket products, typically in natural food sections alongside other alternative protein products. Success requires attractive packaging, competitive pricing, and demonstrated consumer demand that justifies valuable shelf space allocation. Some producers offer in-store sampling programs that allow hesitant consumers to try products risk-free. Food service and ingredient sales to manufacturers represent increasingly important channels as cricket protein gains acceptance. Protein bar companies, snack food manufacturers, and supplement brands incorporate cricket flour into products where insect origins are less prominent. These business-to-business sales move larger volumes at lower margins than retail products but provide production stability and revenue predictability that help facilities operate at efficient scales. Some cricket farms focus exclusively on ingredient supply, foregoing retail branding to concentrate on high-volume wholesale production. Shipping logistics for cricket products are relatively straightforward compared to conventional meat products. Shelf-stable cricket powders and roasted crickets ship via standard parcel and freight services without refrigeration requirements. This eliminates cold chain complexities and costs that challenge conventional meat distribution. However, weight-based shipping charges still impact economics, incentivizing regional production networks that minimize distribution distances. Some producers establish co-packing relationships with regional partners, shipping bulk ingredients for final packaging and distribution near end markets. Byproducts from cricket processing create additional value streams that improve overall operation economics. Cricket frass, the combination of insect waste and substrate materials from growing containers, makes excellent organic fertilizer rich in nitrogen, phosphorus, and beneficial microorganisms. Commercial cricket farms sell frass to organic vegetable growers, nurseries, and home gardeners seeking sustainable alternatives to synthetic fertilizers. Frass typically sells for prices comparable to premium composts, creating meaningful revenue from material that would otherwise require disposal. Exoskeletons shed during cricket molting contain chitin, a polysaccharide with diverse applications in agriculture, medicine, and materials science. Chitin extracted from cricket molts and processing waste has potential uses in biodegradable plastics, wound dressings, water filtration, and agricultural products that boost plant immunity. While commercial chitin extraction from cricket waste remains limited today, research and development continue exploring opportunities to capture additional value from this abundant material. Culinary applications for cricket products span sweet and savory preparations across global cuisines. Whole roasted crickets add crunchy texture and nutty flavor to snack mixes, salads, tacos, and noodle dishes. Their mild taste allows them to adopt flavors from seasonings and sauces, making them versatile protein additions that enhance rather than dominate dishes. Cricket flour incorporates invisibly into baked goods including breads, cookies, pancakes, and energy bars, boosting protein content without dramatically affecting flavor or texture at substitution rates up to 25%. Cricket protein powder blends into smoothies and shakes just like conventional protein supplements, providing complete amino acid profiles with earthy undertones that pair well with chocolate, peanut butter, and fruit flavors. The powder also works in savory applications, including pasta dough, where it adds protein and creates attractive speckled appearance, reminiscent of whole grain products. Creative chefs use cricket powder as coating for fried foods, binder in veggie burgers, and enrichment in sauces and soups. Nutritional value positions crickets among the most nutrient-dense foods available. Cricket powder contains approximately 65% protein by dry weight, exceeding beef at 50% and rivaling isolated plant proteins. This protein includes all 9 essential amino acids in ratios that closely match human requirements. Cricket protein digestibility equals or exceeds conventional meats, with studies showing absorption rates above 90%. Cricket micronutrient content impresses nutritionists familiar with conventional food sources. Iron concentrations exceed beef on a per-weight basis, providing highly bioavailable heme iron that prevents anemia more effectively than plant-based iron sources. Vitamin B12 content surpasses most conventional meats, offering options for flexitarian diets reducing but not eliminating animal products. Calcium, zinc, magnesium, and omega-3 fatty acids round out the nutritional profile, making crickets legitimate superfoods by objective nutritional measures. Prebiotic fiber from cricket chitin supports digestive health and beneficial gut bacteria populations. Unlike most animal proteins that contain no fiber, crickets provide several grams of fiber per serving from their exoskeletons. This fiber acts as prebiotic, feeding beneficial bacteria and supporting immune function. Some research suggests cricket consumption may improve gut microbiome diversity and metabolic health markers. Environmental impact and sustainability represent perhaps the most compelling arguments for cricket farming adoption. Life cycle analyses comparing cricket protein production to conventional livestock reveal dramatic advantages across virtually every environmental metric. Greenhouse gas emissions from cricket farming measure 98% lower per kilogram of protein than beef production, factoring in methane, nitrous oxide, and carbon dioxide from all production stages. Even compared to chicken, the most efficient conventional livestock, crickets generate 80% fewer emissions. Water consumption differences are equally striking. Cricket farming requires less than 1 gallon of water per pound of protein produced compared to over 1,800 gallons per pound of beef protein. This 1,000-fold advantage reflects crickets' low direct water needs and the water-efficient feed crops they consume. In regions facing water scarcity, cricket farming offers protein production possibilities that would be unthinkable with conventional livestock. Land use efficiency allows cricket farming in urban and peri-urban locations impossible for conventional livestock. A single-story warehouse of 10,000 square feet can produce over 100 tons of cricket protein annually, equivalent to the output from several thousand acres of cattle pasture. This vertical farming approach liberates agricultural land for crop production, habitat restoration, or other purposes, while moving protein production closer to urban consumers, reducing transportation distances and associated emissions. Feed efficiency advantages mean cricket farming requires dramatically less cropland indirectly through animal feed production. While cattle require approximately 20 pounds of feed per pound of edible protein, crickets need only 1.5 pounds. This 12-fold efficiency difference means cricket farming could produce equivalent protein for human consumption while freeing up vast cropland acreages currently dedicated to livestock feed production. Some analyses suggest global adoption of insect protein could reduce agricultural land requirements by 30% while feeding growing populations. From selecting productive cricket species and optimizing breeding programs through rapid generation turnover, through sophisticated climate control systems that maintain optimal conditions in vertical farming facilities denser than any conventional livestock operation, to food-grade processing plants where industrial machines transform billions of insects into versatile protein ingredients. meeting the same safety standards as any meat product. Cricket farming represents agricultural innovation at its most transformative. These operations prove that feeding humanity sustainably requires reimagining protein production from first principles rather than incrementally improving systems designed centuries ago. The future of American agriculture and global food security increasingly recognizes that dietary change and agricultural innovation must work together, addressing climate change and resource scarcity. Cricket farming offers both, providing familiar protein nutrition through radically more efficient production systems that work with insect biology, rather than forcing animals into unnatural systems. As technology improves, costs decline, and consumer acceptance grows, cricket protein will increasingly supplement and eventually partially replace conventional livestock in American diets and agricultural landscapes. Thank you for watching this exploration of cricket farming and its potential to revolutionize protein production while building sustainable, climate-resilient food systems. If you found this investigation into next-generation agriculture fascinating, leave a comment below sharing your thoughts on insect protein or other agricultural technologies you would like us to cover.